Okay, so let's do some more examples from some of the problems that were assigned in the textbook. So if you've got more than 2 point charges, or one more than 1 point charge, so number 17 wants to know what the electric potential is. So it says you've got this distribution that shows us 4 different point charges, and they want to know what the net electric potential is. They want to know what V is at this point P. So right there. And there's actually 4 different charges here, right? So I'll number them. I'll say that's 1, 2, 3, and 4. And they all produce their own electric potential at this point. So there's a V1, say, which is K Q1 over R1, which in this case, Q1 is a positive Q. And they all have the same amount of Q. By the way, a femtocoulomb is a 10 to the negative 15 coulomb. And it's D away from point P. There's also V2, which is K Q2 over R2, where Q2 is also a positive Q, and it's also D away. There's V3. Now V3 is Q3 over R3, but Q3 is a negative Q. And this is also DOA. And then finally V4, Q4 over R4. And this is also a negative Q. And now this one's actually 2 DOA. Now what the deal is here is actually the simplest possible thing. The net V is just going to be V1 plus V2 plus V3 plus V4. These aren't vectors. This is not vector addition. Each of these are just numbers, and I just add them together. So rather than writing them out that way, what I generally do is I say, well, all of them are going to have a K. They're all going to have a Q. They all have the same amount of this, and they all have a D of some sort in the bottom, right? And so when I look at V1, I say, well, this is exactly what I have there. This is, right here, is this. And so is V2. Whereas V3 is a negative one of that. It's negative this amount. And then this is a negative 1/2, right? It's got a 2D in the bottom. And then I just have K, Q over D, and I have a number. So I have 1 plus 1 minus 1/2. So this is just 1/2 inside here, right? These two go away from each other, and 1 minus 1/2 is that. And so my value, this is much simpler than actually calculating each of these numbers out. I only have to multiply by the K and the Q and the D one time. So 0.5 times 8.99 to the 9 times 5 times 10 to the negative 15 divided by, and the D is 4 centimeters, so 0.04. And I get an electric potential of 5.62 times 10 to the negative 4 volts. This is the net V at that location. Yeah, so you just add them together. If you have more than one electric point charge, you basically just say the electric potential caused by the first point charge, add the electric potential added by the second, the third, and the fourth. If you've got 6, you just say by plus 5 plus 6. And again, they're just numbers. But if they are negative charges, you have to put in that it's a negative. Now that's the electric potential at that location. The V there is this positive electric potential. If I put a fifth charge at that location, if I put a fifth charge, which is actually a fairly large charge, at that point, what's the electric potential energy? The electric potential energy equation, remember, is Q times the electric potential. So this is a lot like electric field and electric force. Once I know the electric field, I can multiply by the charge and get the force. Here, if I know the electric potential, I can multiply by the charge times the potential, and that will tell me the electric potential energy. -6. This is a tiny potential energy. 5.62 times 10 to the -9 joules. That's just the electric potential energy of that one charge. I mean, if I put a Q5, if it's a negative instead, then again, EQ5, this would be a -10 times -10 to the -6 coulombs. Again, times 5.62 times to the -4 volts. So this is an electric potential energy of -5.62 times 10 to the -9 joules. Now, the electric potential energy of the fifth charge is not the actual electric potential energy of the system. I'm going to write system instead of total. The system, this would be the sum, this would be the total. So when we did UE 2 and we got a number, that was the total electric potential energy of both charges. Here, if I wanted to know, that's the system essentially. Here, what I've just calculated, this is just the potential energy of the one charge. But if I wanted to know the actual E for the entire system, then I have to do the sum of all the pairs. So if I have these 5-point charges, I would actually have to do E12, UE13, 14, 15, and then 23, 24, 25, 34, 35, and 45. All the pairs is what I'd have to do. And that's not the same as what I just calculated. What I have in this number right here, this is all the things that have 5 in it. It's E45, 35, 25, and 15. That's what this is. This is the sum of those terms, but it's not the sum of all of the pairs. That's what we can do here in this example. So here, say I don't want individual amounts. I want to know what's the whole system's electric potential energy. And I have 4 different point charges. What I need to do here is E12, UE13, UE14, UE23, UE24, and then finally UE34. I have to do 6 different terms to do the total potential energy of 4 point charges. Now, again, remember that for any 2 pairs, it's going to be K, Q1, Q2 over R12, not squared, not absolute valued. So when I go through and I do this, they all have a Q. They're all positive Qs too. They're all positive. And so every single one of these pairs is going to have a K, it's going to have a Q squared, and it's going to have an A in the bottom. Some of them might be more than that. So R12 is A. Oh, excuse me. I've got that in the wrong place. R12 is A, R13 is A, R34 is A, and R24 is A. But R23 is the square root of 2 times A, right? It's the hypotenuse of a triangle that has A on both sides. And the same with R14. R14 is also the square root of 2 times A. So they're all going to have an A in the bottom. Some of them might have a square root of 2 in the bottom as well. So if I look at this, UE12 is going to have, it's going to have K, Q times Q divided by A. And so this is just 1 times this term that I brought out. 1,3 is also Q times Q divided by the A, so that's another 1. But then when I get to 1 and 4, I have K Q squared, but I need to divide by the square root of 2. When I get to 2 and 3, this is also separated by the square root of 2. I've got a square root of 2 in the bottom. When I get to 2 and 4, this is also just a 1. And then when I get to 3 and 4, again, it's just A. And so again, I end up with, this is a lot easier in terms of calculating because I'm just going to end up with a number in here. I have 4 plus 2 over the square root of 2, which I can rewrite as 4 plus the square root of 2. 2 divided by the square root of 2 is just the square root of 2. And so I can get that number. 4 plus the square root of 2 is 5.414 times 8.99 to the 9 times 10 microcoulombs squared divided by 0.1. And so this ends up being a positive 48.67 joules. UE for the system is a positive 48.67 joules. This is positive. Remember what we said before, that if we have a positive potential energy, it means that this is a non-bound system, that this is a system that would blow apart if it could. And that absolutely, if I try to put 4 positive charges near each other, they don't want to be near each other. As soon as I let them go, they'll fly away from one another. So they do have a positive potential energy. What is the work done by the electric field to bring these charges together? If they're originally some distance, they were all infinitely far away from each other. So if they were all infinitely far away from each other, remember that the work done by the electric field, electric force, is negative the change in the potential energy. This would be the final, right? What we have here, this is our final potential energy because they are brought together now. And originally they were far away from each other. So what I have, again, the negative change, this means the UE initial minus UE final. So UE initial, if they were all infinitely far apart, then, even if it was just 1 and 2 that were far apart, remember that our equation has K, Q1, Q2 over R. So if R equals infinity, then the U is equal to 0. So our initial potential energy is 0 when R is equal to infinity. So the work done by the electric force is 0, the initial potential energy, minus this 48.67 joules. So it's a negative 48.67 joules. The electrostatic force does negative work here. This is like when you push against gravity, right? The electrostatic force didn't bring these charges together. It wouldn't do that. Electrostatic force would not bring 4 positive charges and bring them close to each other. You had to work against the electrostatic force to make this happen. This is like lifting something up. When we lift something up, the work done by gravity was negative. You remember examples of that where you had the work done by gravity would be negative if you took something from a lower height to a higher height. So you have the work by the electrostatic force here is actually negative, and that's because, and that brings me to this next question, what was the work done by the external force? There had to be some external force that brought these things together. Well, the work done by the external force is negative the work done by the electrostatic force. This is like when we lifted an object against the gravitational force. Right, if we have some object here and gravity is pulling it down this way, but we have some external force lifting it up, and we lift it from some initial height to some final height, the work done by gravity was negative. The work done by the external force is positive, and the work done by the external force is negative, the work done by the gravitational force. So in our situation here, the work done by our external force is this positive 48.67 joules. I think your book may even call this the applied force, applied work. It's possible it calls it that instead of external. I don't know if I can find the actual equation where they did that. But either one would work, external or applied. A little bit more about the relationship between the electric potential. Remember, this means electric potential. And then this is still our electric field. Back in chapter 7, when we first defined work, the work done by a force as an object moves along some path S is actually this integration. But most of the time, our F was constant. And so we could bring it out of the integral, and we just ended up with the work was just essentially the dot product between the force and the displacement, where displacement we've got is S here. In the case of our electrostatic force, this is the amount, this is the force. So we can plug that in for our F here. So our work done by our electrostatic force should be QE dotted with ds. But we've already shown, or we already said, that the work done by the electrostatic force is negative the change in electric potential energy. And so that really ends up with us down here. So the work done by the electric force is this, right? We've seen this back in a couple of examples that we did. So I can set this and this equal to each other. They're both equal to the work done by the electric field, electric force. So I have negative Q V final minus V initial equals QE ds inside this integration. I have a Q on both sides. The Q is constant. Sorry, this should be a negative here. Where did you go? So, and bring the negative to the other side. And so what this says is that if I know some equation for the electric field, I can actually calculate the difference in electric potential between two points. So it's basically, if you know the electric field, say, as a function of like this, then you could actually get the electric potential difference between 2 points. I'll quickly do this problem where we do that type of thing. So number 7 says that in the electric field in a region of space has these components. So what it really is saying, it says E sub x, right? So the electric field can be written, it's a vector, so it can be written in unit vector notation. But they tell me that the E sub y and the E sub z's are 0. E sub y is 0 and E sub z is 0. And so what I really have is an electric field which is only this E sub x. It's 4.00. It's just saying that the units should come out in newtons per coulomb times x I hat, and this will come out in units of newtons per coulomb. So that's my equation for the electric field. It wants to know what's the potential difference between these 2 points where it says V, the point A is up here at, on the y-axis at 3 meters, and then point B is on the x-axis at 4 meters. So I can actually use this equation. So I'm going to say VB minus VA, and it's saying that I'm going along any path that will take me from A to B, any path at all. Well, you know, there's obviously a path to go straight from A to B. But that's a little harder to do the integration of. So instead of doing that, I'm going to split this into 2 paths. I'm going to say, first I'm going to go from here down to the origin, all along the y-axis. And then I'll do another one to here. So I'm going to split this integral. So negative E ds, I'm going to split this into 2 integrals. One where I say I'm going to move along the y. So I say, okay, I want to move along the y. Go moving from 3 meters to 0 meters, and then I'm going to move along the x from 0 meters to 4 meters. Now, both of these have, if I try to do a dot of E with dy, dy is a vector that has dy j hat in it. And so all I end up with here, I'd have to have the EY component. So this would be equal to E sub y dy from 3 meters to 0 meters. And then similarly here with the dx is vector is dx, the non-vector magnitude times I hat. So I need E sub x dx from 0 meters to 4 meters. Let me move this down a little. Nope. So e sub y is 0, right? E sub y is 0. And so I'm just left with here, go back to my purple. So I'm left with e sub x, which is 4x dx, 0 meters to 4 meters. That's a negative 4 integral of x dx from 0 to 4. Negative 4, and the integral there is x squared over 2 from 0 to 4. I end up with negative 4, 16 over 2 minus 0. And this is a negative 32 volts. VB minus VA is a negative 32 volts. So, oh, my thing went away. My question, I think, said, which one is larger, VB or VA? Obviously, VA is larger than VB, looking at this value. Just to be clear on what's happening in that situation. So our VA is actually a larger value by 32 volts than VB. I think I do want to come back and do one more thing here rather than add it in at this point. Actually, I'm going to do this really quickly here, and this may be a little bit over 30 minutes, but it fits in so well. So here we were taking a known electric field function, and we were getting the electric potential. We can do the opposite. We can, if we knew the electric potential as a function, we can actually get the electric field from that. And it comes from the same thing. So the equation I was just using said this, that V final minus V initial, these V's electric potentials are coming from this integration. But I can rewrite this as this integral. That's all that integral is V final minus V initial. Since both of these sides have this same integration, essentially this is from some initial location to some final location, and they're the same places. We're integrating from the same places here. I can get rid of the integration so that all I have is dV on this side and negative E ds on the other. Now negative E ds is this. It's the x part of the electric field with dx, the y part of the electric field with dy, and the z part of the electric field with dz. That's what this dot product is. Essentially, ds is dxi dyj tz k hat. And so when you do this dot product, you just end up with these products added together. What that means is that the Ex, the x part of the electric field, is negative the derivative of the voltage equation, the electric potential equation with respect to x. The electric field in the y component of it is that partial derivative with respect to y, and then the z is the same sort of thing. So for number 35, they tell me that the electric potential has this function. I can write the electric potential as this function. I'm going to leave the units out. So 2x squared minus 3y squared. So it doesn't actually depend upon z at all. So I can get the electric field in the x component of it by taking the derivative of this with respect to x. And so these are just partial derivatives. Hopefully you've gotten to that. It just means let's pretend like the y is constant. So when I take this partial derivative, I end up having 4 times x, and at x equals 3 meters, this E sub x equals negative 12 volts per meter. I can get the y part by taking the partial derivative with respect to y. So again, now I go back and I look at this equation. That's going to be a negative 6 times y at y equals 2 meters. E sub y is this would be a positive, right? Because I have a negative, actually this should be a negative. And I did get that to be negative here. And then this should be a positive. I have a negative times a negative. So this is a positive 12 volts per meter. And then E sub z is the partial with respect to z. Well, there isn't anything. It's a constant. It's in respect to z. And so my electric field at x equals 3 meters and y equals 2 meters is a negative 12 volts per meter in the I hat direction and a positive 12 volts per meter in the j hat direction. Okay, I do have a little bit more that I'm going to do on chapter 24, but I'm going to save that for next week's pre-recorded lectures. It's essentially when we spread charge all over an object, which is number 25. Is the one problem that I'm having you guys do with that. I may have time to do that during the week. We'll see, or else I'll just do it on the Monday when we come back next week for Monday. All right, this has been a lot. We are really in the thick of it. This is going to take a lot of work on y'all's part to try to grasp it all, but it is all doable, and we'll work on it during class as well.